In this video, we'll talk about concavity, what it looks like in terms of the graph of a function, and how we can find it using calculus. So, what do we mean by a concavity? Well, we say a function is concave up if, in an informal sense, if the graph sort of curves upward as you move to the right. In a more formal sense, we say this is the case if the graph is always above its tangent lines at nearby points. So in terms of a picture, this looks something like this. I have a parabola like that, and I take some tangent line at a point here. The graph of the function is always above that tangent line. But the tangent line's down here, and the function sits above it at those points. Now, how does this work in terms of actual calculus things to actually figure out about this function? Well, if I want to be above the tangent line, the function has to sort of grow faster than the tangent line as you move to the right past that point. What this really means is I need the slope of the curve to be higher than the tangent line as I shift to the right, and then lower as I go to the left because it has to come in above that as well. Well, what does that mean? Well, the slope of the tangent is the derivative, and the slope of the curve is still the derivative. But this means that my derivative needs to be increasing if I'm going to stay above the curve, because that's going to force the slope of the curve getting bigger than that of the tangent line, which is the derivative point, as I go through this point. So this means the derivative needs to be increasing for me to be a concave up function. The conclusion from all of this is that f is concave up if f prime is increasing. Now I want to work this towards something we actually use to figure out if a function is concave up or concave down more directly. So for our definitions now, what we really have for this is that f is concave up on some interval ab if the derivative is increasing there. And we have a similar definition for concave down, which is the curve is bending downward. And again, the same thing applies, and it requires that f prime be decreasing on that interval. How can we get this more directly? Well, we know what it means for a function to be increasing or decreasing. Right? If a function is increasing, its derivative is positive. So if I want that f prime is increasing, that should relate to f double prime being positive, because then f prime's derivative, which is f double prime, is positive, means the function itself, which is f prime, is increasing. And similarly, for f prime decreasing, I will want f double prime to be negative for the same logic as above. So this gives us our actual test for concavity. We'll assume that f is twice differentiable, so it has two derivatives. Then what happens? Well, if f double prime is positive on AB, then my function is concave up on that interval. And similarly, if f double prime is negative, my function is concave down. And you can use this the same way you would talk about stuff for increasing and decreasing functions to figure out intervals where certain functions are concave up and concave down. So as an example, let's look at where the function x minus 2 times 1 minus x cubed is concave up and concave down. To do this, we need the second derivative. And to find that, we're just going to expand out into a single polynomial and differentiate that twice. So expanding this out, f of x is x minus 2 minus x to the fourth plus 2x cubed. This is a polynomial, so I just differentiate it twice. Our first derivative is 1 minus 4x cubed plus 6x squared. And our second derivative is negative 12x squared plus 12x. To figure out where it is positive and negative, I want to look where it's either 0 or doesn't exist. In this case, the polynomial should always exists, so I can find these transition points by just setting this to 0. And if I solve this out, I can divide through by a 12. Negative x squared plus x equals 0, or x times 1 minus x equals 0, which means my points that I'm caring about here are x equals 0 and x equals 1. We can again draw a number line here for f double prime to figure out where it's positive and negative. We know the points we got to mark are 0 and 1. I can just plug in my second derivative here. If I plug in 1/2, this here has the same sign as my second derivative. So I plug in 1/2, I get a positive number. It's 1/2 times 1/2. And I'll get a negative number on the two outsides here, plugging in minus 1 and 2. So then I know that I am concave down wherever I see a minus sign and concave up wherever I see a plus sign. So I will then get a conclusion that f is concave up on the middle part here from 0 to 1, and f is concave down on the other two parts, minus infinity up to 0, and from 1 to infinity. That's the idea of concavity, what it looks like in terms of functions, and how we can use calculus, in particular the second derivative, to figure out where a function is concave up and concave down.